Hi everyone, back in a new awesome video, and today we're going to continue with our series about electricity and magnetism. Today we will start with a series of videos of 3 videos about electric potential. In this video we will introduce formally this quantity, we will also talk about its 0 point and superposition of it, and finally we will relate it to the electric field. So let's start. Great, let's introduce formally the notion of electric potential. Last time, if you recall, we introduced electric potential energy, a magnitude we represented with the letter U as its potential energy, and we equated it, the change of it was equal to minus the work that had been done. And this is a path integral, we all know, which is from A to B of the force, that it may depend on position, as this is a vector field, and times the path. This is a dot product. And by doing this, we were able to find in different situations what the change in potential energy was. And we also developed some formulas for it, and we ended up getting this situation in which we were able to find a formula in terms of the position B and in terms of the position A to find the difference. However, if you recall from our earliest videos in this series, we introduced the notion of electric field, and we did that because to have a force, we need to have two charges. However, we may consider also a situation in which we just have one charge, and this charge generates some sort of field, an electric field we called it, around it, and then all the other charges interact with that electric field. Therefore, we're going to do something similar with this electric potential energy, so that one charge generates some sort of electric potential around it, and the other charges are going to interact with that electric potential, and we can also use that to find the electric potential energy. So similarly, we're going to have a magnitude B, the electric potential, and the change in B is going to be equal to minus the work divided by a test charge, because if you remember from our earliest videos, what we did was having the force divided by the test charge, and they effectively cancel each other because there's a factor of the test charge inside of the work right now. And now this is going to be the integral, the path integral from A to B, not of the force, but of the electric field. This is also probably going to be dependent on R. And we end up getting, in a very similar manner, the same formulas. Well, pretty close formulas for this situation. Now it's also interesting to analyze what the units of this electric potential is going to be. You can see from here that is going to be the units of the electric field times the units of distance. So it's going to be the units of electric field times the units of distance, which, if you recall correctly, this is newtons over coulombs times meters, and we can combine newtons and meters to find joules. So the units of the electric potential are going to be joules over coulombs, and this makes sense because we want it to be something that if we multiply by a charge that is that electric potential is going to give us an energy. So this is a very important relationship, that any potential energy, it's equal to the test charge times our voltage, because that's what this is called. And furthermore, there is a special name for this unit, as it's the voltage. We measure it with volts. Final thing we may want to do is that we can express work, which used to be a combination of, well, external work. It's a combination of the change in kinetic energy plus, instead of our usual electric potential energy, we will express it in terms of our new electric potential, which is going to be a much more useful thing because we can find this electric potential regardless of what charge we have and input that charge later. So it's much more useful in lots of physical applications. Alright, now there are some questions that we have to answer about electric potential in a similar manner to what we did with electric potential energy. We'll start having, for example, a small charge we're going to call QS over here, and we're going to have some sort of path that goes around here, in which we will put our test charge and we will move it from point A to point B. Now, knowing this, we know from our definition that the change in potential equals minus the integral from A to B of our electric field, which is dependent on position, times ds. Now, we are going to take this to be our origin, so this is our origin and the charge is on it, so that things simplify a little bit. Now, if this is the origin, we know what the electric field is at any point, so we will write that. It's minus AB from K QS over R squared times ds, and this is an R hat vector. And if we solve for this, we realize that the only thing that matters is going to be the displacement in the r hat direction. Therefore, what we are going to have is that this is an integral from minus a to b of k qs over r squared dr. We have a lot of constants in here, so we may go minus k qs, and 1 over r squared, it's minus 1 over r when we integrate it from a to b. So we realize also that the only values about a and b that we care about are the distance at which they are from the charge. So we could get a formula for example, well, let's write it all, and we would get the minus with the minus cancels, and kqs over ra minus this should be rb minus kqs over ra. And we may recognize in here the potential at B and the potential at A. So we could say that the potential, electric potential at the point B equals kqs over rv. By knowing this, we are now able to find the 0 point, because what we are going to assume is that, for example, Ra is going to be at infinity. So we will say that at infinity this equals 0, and that way we make sure that there are no constants that we have to add here. If we, for example, say that this is equal to 1, we just will add a constant over here, which will really don't do anything, because what we care about is differences in most of the times. However, this is a much nicer form to have than having an extra constant here, which really doesn't play a role and it's totally arbitrary. So now we have a formula for our potential energy in any place, the electric potential in any place, and we realize that it's pretty analogous to the one we had with electric potential energy, which was the same thing but without the other charge, which I'm going to call test because that's where it arises from. So we can see the relationship we talked about in the previous segment, that multiplying this by the charge, test charge in this case, will recover the electric potential energy. Another thing that we have to take into account is that this is going to generate a scalar field, a field in which every point has a value of electric potential. And if we have different charges that are going to be generating these fields, we're going to have a superposition of electric fields, as we talked about that. And thankfully, integrals are distributive, so you can have addition of multiple integrals instead of adding them inside the integral. So what that means is that the principle of superposition also applies with electric potential. That is that the total field generated because of 90 charges equals V1 plus V2 plus da 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 plus V90, and it could go on forever. So electric potentials follow the principle of superposition, and to find the total one, we just have to add the different ones generated by each charge at a specific point of space. Great. Now let's try and relate this to electric field. I don't know if we have covered it yet, but we will cover it for sure in the future in our classical mechanics series. And that is that force equals minus the gradient of the electric potential energy, or the potential energy in general. And there is something pretty similar that happens with electric field and the electric potential. We find that the electric potential equals minus the gradient of electric potential. So if we will draw some points at which the electric potential is the same. So those are going to be concentric circles because the electric potential only depends on the distance from the particle. So imagine this is a circle with a particle in the center, in the middle. And we're going to have lots of them that are going to have different values of V. We may have one closer over here. They are becoming less of a circle over time. And what we know from this definition is that the electric potential is going to be perpendicular to these lines. In fact, these surfaces, because this should be 3D and we would have a sphere, another sphere, and all of that. So they are going to be perpendicular to these lines, to these surfaces that are called equipotentials, points of the same potential. And if we try to draw the electric field, we'll say this is a positive charge. What we are going to have is field lines that are going to point perpendicular to these surfaces and to all of them. And this fact is represented mathematically by this statement, that the electric field is minus the gradient of the electric potential. That is all for today. I hope you had a basic understanding of what electric potential is, and also its relationship with electric potential energy, and also with the electric field, because they play analogous roles in different places. Any doubts left, you may ask them on the comment section, and I'll try to answer them in the best way I can. Remember to like the video if it was the case, press the subscribe button, the bell, and follow us on social media so that you don't miss any of the new videos. See you another day with more Physicawesome!